Welcome to Finite Element Methods. Today we'll be discussing the minimization of functionals, and we will be using the Ritz method to be able to solve problems in structural mechanics. And this can be also applied to heat transfer as well. So there are three approximation methods that we have discussed in this course. The first one is a strong form Galerkin. The next one is a weak form Galerkin. And then the one we'll be discussing today is Rayleigh-Ritz method. And this method is really convenient when you have the functional of a problem. I'll try to explain what that means. So what is a functional? In this type of discussion I'll be discussing today, this one is typically reserved for a graduate level class, but I have to provide some context on what this is. So what is a functional? A functional is a function of a function. And I'll explain what that means. So for example, take a curve of length L, and you can see here I have a curve which could have a length L. In this problem, we consider this a functional because in this case, the length of that curve depends on the shape of the curve. So if the curve was straight, the length will be smaller. If the curve was more curvy than what you show, then the length L will be larger than what you see in the screen. So uh, one of the questions that comes up a lot is one of the questions that could come up is given a chord of length L, what shape of the curve minimizes the distance between the ends of this curve? And we know that that's a straight line. But to get to that answer, you have to approach it in a very particular way. So I can calculate the distance of a small differential element and integrate that over from x equals 0 to x equals a, say. And that will give me the length as shown in this equation. What you see here quickly is that the length depends on y, and y shows up inside this square root. And we have to find that y that minimizes L. This is a functional. L is a functional because L is a function of another function. What you may have seen back in school was something a little bit more different. You may have seen something like y of x equals 5x squared minus 4. And somebody asks you, hey, what is the value of x that minimizes y? And so you just do this derivative of y respect to x, and that gives you 10x minus 0. And then you will have say, okay, this is equal to 0. Okay, you will have done something like that. And then you will have solved for x. And they'll have given you the minimum value of x that minimizes y. That's very simple. But when I'm talking about finding a function y that minimizes L, that's an entirely different question. You can't just do the root of L, which depends on y, right? I can't just do the root of L respect to y of x equals 0. I can't do that because that's not how that works when a function depends on another function. You have to find an alternate method to go about it. Now, in this course, I cannot go into that level of detail because that's covered on a more advanced course. However, I have to bring it up because finite elements uses some of those ideas. And so let me start first discussing the idea of the total potential energy. Every body of material is going to have some amount of total potential energy. And that's going to be composed of the strain energy stored in the body plus the potential energy from applied loads. Now, you may have seen in the previous lecture when we covered the spring that a spring has some amount of stored energy. And that stored energy can be written as U equals 1/2 K delta squared. We covered that. And then we have a potential energy of negative 1/2, sorry, negative the load P applied times the deflection at that end, right? So the total energy, potential energy for a single spring is pi equals U plus V. So we covered that in the previous lectures. But what happens in a 3D body of material where stresses and strains are acting on the body of material? The idea there is then you do have a strain energy, and that strain energy is going to be equal to the integral over the whole volume, and is going to be the stress in each direction multiplied by the corresponding strain in each direction. That's what we're talking about here. And you also have the stress times the strain uh, in the y direction and the z direction, and the shears as well. And that's the strain energy stored in the body of material. And that matters when we're looking at these kind of problems. The other thing I want to point out is if you examine this term, notice how if this is sigma xx, and I went to the instrument machine and did a test, I will find the following. I apologize. That 1/2 sigma xx epsilon xx is really the area under that curve. And that's what you see there as a strain energy. And that makes total sense. The strain energy is the area under the stress strain curve. And that makes sense. Now I have to integrate this quantity over the volume because I need to determine the total strain energy in that volume material that has volume V. Now recall from the earlier boundary value problem lecture that the stress vector, which is composed of sigma xx, sigma yy, sigma zz, sigma xz, sigma xy, and sigma yz, recall that that stress can be written in the vector sigma bold that you see here. And that I can multiply that by epsilon bold, which contains these strains, okay? I can put that here into that. And I'm simplifying it. Instead of writing that whole thing at once, I can write it in matrix notation because it saves me time. I don't have to write all that. And we found from the previous lecture I can do that. And so stress bold times epsilon bold is exactly what you see above. Is exactly what you see above, is no different. And so this right here is equivalent to that. And now remember that stress bold is equal to the stiffness matrix times the strain, the stiffness of the system times the strain bold. So that's what goes in there. And now this has transpose, and I can apply that transpose over this whole thing. And when you do that, everything switches around and you get epsilon bold T, C bold T, and epsilon bold. And this is discussed in my book in one of the last chapters for 3D bodies. I go into that in more detail. Now, the stiffness matrix, this stiffness matrix, which relates stress to strain, stress equals C bold times epsilon bold, that relationship can be calculated. You can calculate C bold from experimental evidence. And what the other thing you'll find here is that the C bold that we have previously discussed, the examples that I showed you shows that C bold transpose is the same as C bold because the stiffness is symmetric. That's why. Okay. And yeah, so we have that. So very neat. And the strain energy is simply the area under the curve. I already covered that. I already showed you that in the little diagram pointed there. Um, but yeah, so that's the strain energy of the whole body of material in 3D. And now I want to look at what's going on with the types of loads that can act on the body of material. You could have a point load acting in this body of material. You can have a gravitational load acting in this body of material. You can have tractions acting on the surface of this material. These loads, these three types of loads, are going to cause a potential energy. Okay? And that potential energy needs to be added to the strain energy to calculate the total potential energy. And the potential energy due to applied loads can be quickly determined. So I have that body of material, that body force, which has vectors bx, by, bz, because the body force can be acting at an angle. Bx times u plus by times v plus bz times w. And since this is a body force, is per unit volume. So that's acting at every point in the volume. So therefore, it needs to be inside in an inside volume integral, like you see here. So bxu plus byv plus bzw is integrated of the whole volume gives me a total potential energy due to the body forces. And then I have the tractions acting just on the surface. The tractions acting just on the surface is the same thing. A traction vector acting at a particular point on the surface at that point in the surface has to be multiplied by the deflection in that same direction, ty times v plus tz times w. Remember, the traction has three components of tractions, tx, ty, and tz at every point on the surface where I do apply them. And then the body forces can also have directional components, and that's why they need to be multiplied by uv and w in their respective directions. Instead, I have a point load somehow that's applied. You can take that point load, which is a vector quantity, and decompose it in the x, y, and z directions, and multiply each of those directions by the deflections u, v, and w. And this gives you the potential energy due to loads applied. Basically, the work done due to loads applied. Okay, so that's what we get. We have not only we have the strain energy, the total strain energy due that's stored in the body of material, but then we also have the potential energy due to the loads applied to the structure. So when I look at the whole thing together, the total potential energy is the strain energy stored in the volume of material and plus the potential energy due to loads applied. And this is not very different from when you probably saw this before in physics, that you could have this situation where I have this block of material, I apply load P, and if this moves an amount delta, then the work done W is P times delta. That's what you're seeing here, right? That's exactly what you see there. That's exactly what you see there. That's exactly what you see there. Nothing different. The reason you see these integrals is because the body force is acting at every point inside the body of material. Like gravity acts, when gravity acts on your human body, I hope gravity acts not only on the hair, not on just on the feet, not just on the outside of your body, but it acts on every point inside your body. And as a consequence, there needs to be a volume integral. The tractions, such as lift, drag on an aircraft wing, that acts on the surface of the material that encloses that body of volume V. And as a consequence, that traction multiplied by the deflections, corresponding deflections, becomes extremely important to also consider, okay, in your assessments. So so here note how this is so analogous to the idea that I showed here, where the length depends on y and y is a function. Very similarly, I want to show you that that's what we have here. We have a total potential energy pi that depends on u, v, and w, but u, v, and w are functions because u is really going to change depending upon where you are, and the same with v and the same with w. U, v, and w are the deflections of the body of material, and they are functions on their own, right? So pi here is a function of other functions, and therefore pi is considered functional. And the print this idea, okay, and I cannot derive in this particular course. I have that some of that in my book, but in a more advanced course, you will learn that there's this idea called the principle of minimum potential energy, and it's an amazing principle that's going to open your eyes today, and it's going to show you how this is so equivalent to what I just discussed in the previous lectures when I was deriving the elastic bar equation and the beam equation. In reality, the principle of minimum potential energy is telling us that you have a lot of deflections that could occur. So if I have a beam of material in 3D, just consider 3D problem, okay? If I have a number of deflections that could occur. So I apply a load here, bam, great. We know this is going to deflect. this way. I hope you know that it's going to deflect that way. But I think everybody could agree there's infinite number of ways that this beam could potentially deform. And what this principle of minimum potential energy is telling us is that there is a set of deflections, a unique set of deflections that minimize this pi. So there is a set of u, v, and w, a particular set of deflections u, v, and w that cause that pi to be a minimum. And for that to occur, that only occurs if you satisfy the governing equations of elasticity of this body. In other words, the body is in equilibrium. So perhaps the deflection of this beam is like this. And you said, no, that's not the deflection of the beam. Yeah, I agree. But if I were to plug in u, v, and w in here into this equation, pi will be larger than in the real answer, which is, we know the real answer looks like this, not like this. But if I were to plug something else, pi will be larger. And what this is telling us is that the real solution to these solid mechanics problems is one where u, v, and w minimize pi. That's what we're saying there. And I know it's a very abstract concept, but it's not very different from what I showed you for the spring element. If you recall, pi for the spring element was 1/2 k delta squared minus p times delta, where k was a spring constant and p was a load applied. Recall that in that example, that's what I had. Okay. So the derivative of pi with respect to delta is set equal to 0 to find which delta causes pi to be a minimum. And what you find here is that you get 2k delta divided by 2 minus p equals 0, and so you get p equals k delta. Isn't that the equation that describes how a spring will deflect under a load p? That's exactly what you learn in physics. We're saying the same thing here, that if I were to find the solution u, v, and w for a particular problem, that u, v, and w cause pi to be a minimum, for the body to be in equilibrium, for the governing equations to be satisfied. And that idea is not very different from when I covered this. So which y is the one that minimizes L? That y is a straight line. We all know that. We know that the minimum length here occurs when I have a straight line for y. That's the bottom line. And we all know that. But if I were to select a y that was like more messy, we know that L will be larger. In a very similar fashion, that's exactly the idea that I have in mind when I'm discussing this total potential energy idea. Okay? Not very different. The idea there is we're saying there's a u, v, and w that not only solve the governing equation for a particular problem, but that is the right set of deflections that also minimize pi. And so I hope that idea is clear. I hope that idea is clear. And please do ask me any questions you have. In case I didn't say it, the load P is a point load applied on the surface. But you can have many of them. I just drew one. You could have many of them. I just drew that for illustration purposes. But P, there's a single load P that I applied, and that load P is a vector that contains these components. And the deflection vector is, and the work done due to the load applied is this, which is exactly the minus of that, which is exactly what you see there. The dot product of the load vector dotted with deflection at that particular point. Okay, so that's what that P is. And so I do want to point out that total potential energy only exists for conservative systems. If the deformation is elastic, meaning that when you remove the load, it's going to come back to the original state. If the loads do not depend on the deformation of the system, That means that the load is conservative and not a follower force. For example, in this case, if the force continues to be tangent to the axis, then the total potential energy does not exist. My book goes into some of that and shows you alternate ways to get there. So let's look at the total potential energy for 1D elastic bar. And I don't want to necessarily have you become an expert on how to derive the total potential energy. Um, and in the book, I go into details on how to do that if necessary. But I already kind of covered this already, so I expect everybody here to kind of understand it at least. And so, if you recall, for an elastic bar, we have demonstrated that epsilon xx equals partial u partial x, where this is also u prime. I could just call it u prime. And if I apply the idea of total potential energy for this 1D elastic bar, as you're seeing in this picture here at the top, we don't have sigma yy, epsilon yy, sigma zz, epsilon yy, zz. We don't have any of the shears because in 1D elastic bar, we discussed how these kind of structures can only support axial loads along the bar, like truss elements. And so, as a consequence, you will see that in this particular example, we've eliminated all these terms that don't exist. Okay, and in the example I'm showing, we do have traction loads, but they only act in the u direction. So so these are not present, and we don't have any body forces in these examples. We do have this load applied on the left hand side and right hand side. So you can see here how quickly this simplifies into this equation here that you see. So you have 1/2 sigma xx epsilon xx from the previous slides. And then you have this force that's applied distributed to this. And that's Q bar. I'm going to call it Q bar times UdA. Minus PL times U at L, because that's the load applied here at this end. Minus P naught times U naught, U at 0, because that's the load applied to this end. And here note that I'm defining Q bar times B, which is the width of that elastic bar, to be Q. Okay, it's a little trick. And now what I want to do is, I know that sigma xx, we all know that sigma xx for 1D, and you saw this in school probably, mechanics of materials, hopefully, we know that sigma xx equals E times epsilon xx. As a consequence, this right here turns into E times epsilon x squared. So we clearly have that. I think we can all agree to that this turns into that when applying this constitutive relationship. I also have this as similar that nothing changes here. What we notice here is that epsilon xx is u prime, and that's only a function. Recall that u is only a function of x in for a bar. It does not depend on the cross section d dv da d sorry da, which is dy dc. And so as a consequence, um, we have a scenario. I apologize. As a consequence, E, A could depend on the length, but they don't depend on dy and dz, which is a cross section. Epsilon xx clearly does not depend on y either, or z. So therefore, you get the integral from 0 to L, and this dv, which used to be dA dx, you just get the integral dA, and that's a, right? So it simplifies to 1/2 EA u prime squared dx. And if I integrate Q bar along the width of the sample of the bar, I get Q U dx 0 to L, because that's the boundaries of my problem. And this stays the same. So that is the total potential energy for the 1D elastic bar. And so how do I find U? How do I find U that minimizes pi? I want to find U that minimizes pi. That's the idea there. And the idea there is to, this looks messy, just a second. The idea is to minimize a functional. And what we want to do is minimize pi. We have to find u that minimizes pi. How do we do that? So the idea here is to compute the directional derivative along an arbitrary function v. That's the idea. So if I select an arbitrary function v, some function v of some kind, and I multiply by some scalar value epsilon, and epsilon is very small so that v is in the neighborhood of u, is very close to where u is at. If I were to find this derivative respect to epsilon and set that equal to 0, then I may be able to have a chance of finding what u minimizes pi. And this can be derived using Taylor series expansion. Now, this idea of why this works is covered in more advanced course uh, that I'm not going to cover today. You can find YouTube videos on this, and the course is called the Energy Methods and Computational Mechanics. But I don't want to spend too much time into that. I'd rather just tell you that there's a way that gives you the path of finding the u that minimizes pi by calculating this directional derivative. This type of derivatives you may find when you do optimization problems as well. So it's not very different from that idea. And again, the idea is to take u and add a small amount and that small amount is an arbitrary function multiplied by a scalar quantity, and the idea is to find somehow this derivative, set it to 0, and then hope that can find u that minimizes pi. That's the goal there, and I want to show you how that can be done, okay? And to do that, what I'm going to do, I'm going to substitute, instead of this u here that you see there, I'm going to plug in here u plus epsilon v. And here I'm going to put u plus epsilon v. And here I'm going to put u plus epsilon v. And here u plus epsilon v. Okay, that's what we're going to do. And that's exactly what I've done here. You can see that there. I plugged it in. Okay. This used to be u prime, if you recall. This used to be u. This used to be u at L. And this used to be u at 0. Very nice. And so that's the same thing I had here. Okay. Not different. I just swapped u for u plus epsilon v. That's all I did. To evaluate that. Okay. And so this looks less messy. What I'm going to do, I'm going to delete this so it doesn't look as messy. And I'm going to expand. So you can see here that this term here becomes u prime squared plus 2 epsilon v prime plus v prime squared. This term right here becomes u plus 2 epsilon v plus v squared. And so on. Now, I have to find this derivative respect to this whole thing and respect to this whole thing. What you notice is that there's no epsilon here, so this goes away when I find that derivative. This goes to 0 when I find that derivative because that has no epsilon, and I have to find that derivative. The derivative of this one here, this has no epsilon, that goes to 0. This has no epsilon, goes to 0. I only have this derivative that I have to take care of, and that's just 2v prime, and that's just 2v. Same thing here. There's no derivative there to worry about. The derivative of this is just VL. The derivative of this respect to epsilon is 0. The derivative of this respect to epsilon is just V. So you just get that. And so I've been able to do a good job of doing that, those derivatives. One thing I actually did mess up, I did mess up big time, and I want to fix that so you don't get confused. But this epsilon squared v prime, and I messed up. It's not going to 0. That has epsilon. Okay, my bad. So when I find the derivative of this, though, I get 2 epsilon v prime squared. And on this one, I get 2 epsilon v. Okay. Yeah. So this actually, you're right. You're right. Again, another error on my end. So thank you. So this is not squared. I apologize. So that stays the way it is. But when I find the derivative of that respect to epsilon, this goes away, and I just get v for the derivative of that. What you notice here is that I have to evaluate this epsilon equals zero. So you see here that this term, when I evaluate epsilon equals zero, goes away. Um, and I'll just show you what it looks like. I think you should do it at home. I just did it really quickly here so you can kind of see the procedure. First, expand all the derivatives, set it to zero, and then work it out. And you can see here when I do it, look at this. I expanded this whole thing. I don't have to expand that. You're right, it's not squared. That's this. Nothing there, nothing fancy there. Um, Now I take this derivative. Let's do it. So when I take this derivative, it goes to zero. That goes to this one. This one goes to this one, respect to epsilon. And then this one, respect to epsilon, that goes to zero. That doesn't show up. This one turns out to be this one. And then this, the derivative with respect to epsilon again, that's just v, and that's just v. That's it. Now I evaluate this epsilon equals zero. So this goes to zero. These two cancel with that two. That's pretty much it. This is what I get. This is what I get. Now there's something interesting when I look at this. I want you to go back to the weak form of the problem when I had the elastic bar problem. And you're going to see from last week's lecture that the weak form actually matches this equation you see right there, which is a mathematical miracle. Why? Because when I developed the weak form, I started from the governing equation for an elastic bar. And I developed the weak form and I got the exact same thing you see on the screen. Now I start from the total potential energy. And to minimize the total potential energy, what I find is that I get the weak form. So it's almost like they're connected somehow, and they are. So if we derive the weak form from this differential equation, if you recall, what we talked about was to form the weighted residual. So to do that, multiply the whole thing by v, which you see here. We talked about integrating by parts, so we can share the order of differentiation, right? If you recall, um, and that's what I did. I put the v here, v prime, eau prime, prime has to be put here. I remove one of the primes, I get this, and then plus minus, and we know the bottom one goes here. This cross term goes here. Now, in this problem, we have already talked about uh, that I should multiply by minus one. If you look in my book, I explained that it's better to have this as positive to start with, which is fine. You can do that. Nobody's going to stop you. But all I've done is notice how this here is an essential boundary condition. This right here is PL. This right here is P naught. And so I get the weak form, which is this. Starting, look, I started from the governing equation of the problem. This is what you find in mechanics materials book for an elastic bar. And I applied the weak form, I developed the weak form, and notice how I got to this expression here. Isn't that expression the same expression I got by minimizing the total potential energy with respect to U? This equation right here matches the weak form. It matches this. So minimization of total potential energy leads to the weak form of the 1D elastic bar. That is, minimization of the total potential energy also implies that the elastic bar is in equilibrium. Why? This equation right here is connected to this equation right here. That is the equation that describes the equilibrium of a bar. And that equation is connected to this equation. But this equation is also connected to this equation. They're all interconnected. So minimization of total potential energy gives me the weak form, but the weak form was derived from the elastic bar equation that you see in the mechanics materials. So using the potential energy, I'm able to connect it all the way down to this differential equation using an entirely different method that has been discussed in this course. So that's an amazing thing. It's connected somehow. Everything's connected. Weak form and the minimization of the total potential energy is connected. Therefore, that's a mathematical miracle in it on its own right. Just looking at that. Okay. So that was a strong form of an elastic bar. I can use a weak form to develop this. But guess what? If I minimize the total potential energy, I also arrive to the same expression. Then when I take the strong form and develop the weak form. In other words, this minimization of total potential energy also implies solving this equation. So minimization of total potential energy also implies that I'm solving this equation. In other words, okay? And that's a mathematical miracle, okay? Now let's look at the elastic bar problem. For the elastic bar problem, the total potential energy for this problem, again, sigma xx epsilon xx, sure, because I don't have any transfer stresses for Euler-Bernoulli beam, as I had discussed previously. The transverse load is Q, so that's times W gives me the transverse load, the potential energy due to applied loads. That makes sense. Q times W. W is a transverse deflection, and Q is also acting in the same direction, so that makes sense. Minus W at L times Q3. That makes sense. That's the deflection going upwards. The error is missing, but that's the deflection going upwards, and that's W also going upwards at that location. Minus W naught times Q1, which is the deflection here times Q1 over the load applied there. That makes sense. Minus W prime at L, Q4, which is this moment here. So the slope is associated with the moment, minus the slope times Q2 at this location. That's the potential energy due to applied loads, all this stuff here. Well, that's the strain energy. Now, the same thing applies. Stress equals, in one-dimensional theory, stress equals E times epsilon xx. So I get E times epsilon x squared. And this term stays the same. Everything stays the same. Now, I know that epsilon xx, if you go back to the boundary value problem lecture, you'll see that I said that epsilon xx is equal to y times w double prime. So epsilon xx is y times w double prime, and where w double prime is the curvature. So I want you to revisit back to the boundary value problem lecture so you can see this was true, and I don't want to rederive it. W is a function of x alone. It's not a function of y because we're only looking at transverse deflections. And it does not depend on z either, the thickness. So we can do something similar as I did before, where E and W double prime can be taken outside of the dA integral. Now notice how W double prime has to, how y has to stay inside the integral because dA does have dy and has dz. Everything else stays the same. This term becomes q because I integrated to the width of the beam. And you can see here how, just recall how the integral of y squared dA, the integral of y squared dA is the moment of inertia. So I'm going to get the total potential energy to be 1/2 EI W double prime squared integral y squared dA. Now this I should not have shown there, so I apologize for that. That was too premature. Um, so I can take E and W double prime outside of the dA integral, but I still have to keep the dx integral. Now this is I. This whole thing is I, moment of inertia. And so notice how the rest also stays the same. So that term now becomes EI, W double prime squared. This term is this one, and this whole thing shows up here. So that is a total potential energy derivation for the 1D elastic beam theory. I'm not going to ask you to derive them in this course because that's actually done in a more advanced class. But I want to show you how this is equivalent to the weak form again, once again. So again, what I'm going to do, I want to find W that minimizes pi because the W that minimizes pi is the one that solves the governing equation for the beam, and that's the one that minimizes pi. Okay, that's what I want to do. I want to find what W minimizes pi. So to do that, I already told you I have to take W and added a small arbitrary function. Um, and I'm doing that by putting a very small infinitesimally scalar quantity epsilon multiplied by this arbitrary function, be sine, cosine, whatever you want it to be. But I want to take this derivative, this directional derivative, set that to zero, and then equate that to zero, and that will give me the equation that when solved for W minimizes pi. And I did it here. So again, I took anywhere I saw W, anywhere I saw W. It looks very messy, but it's not. Anywhere I see W, I plug W plus epsilon, V. That's all I do for every single one of these W's. And that's what you see here. I plugged in anywhere I see W, I plugged the whole thing there. And then I expanded this expression. Sure. There's nothing to be squared else, so everything else is the same. And then I take this derivative, which I can do fairly quickly. So if I take this derivative, this goes to zero, right? That goes to zero. This becomes one. This becomes 2 epsilon v double prime squared. This goes to zero. This becomes v. So this becomes 1 here. And then I notice that when I plug in epsilon equals 0, this goes away completely. And I'm done. And you can see here that I get this equation right here at the bottom when you do it. Isn't that the weak form that resulted from when I did weak form last week for a Euler-Bernoulli beam? Again, amazing. I started with the total potential energy, found which W minimizes pi, and guess what I end up with? I end up with the weak form of the problem that I developed starting from the strong form. Again, I started from here last week. I developed the weak form and I got that. But today, I started from here without looking at this equation at all. I got to this point today because the W that minimizes pi is giving you this equation, and that equation looks like the weak form to me. And guess what? I derived this weak form from the strong form. Therefore, this equation, this implies this also. If I solve for W out of this equation and plugged it in here, that's the one that minimizes pi also. So isn't that beautiful? Isn't that exciting that we got to the same answer with entirely two different methods, right? And that's an amazing thing that we need to discuss. In both examples, in a conservative deformation process, the minimization of the total potential energy is a weak form of the problem. Since the weak form of the problem is derived from the strong form of the problem, then the minimization of the total potential energy also implies a strong form of the problem. Therefore, approximating the solution to the PDE using the weak form Galerkin can also be accomplished by substituting an admissible approximate solution into the total potential energy and minimizing the total potential energy with respect to the unknown coefficients. And this method is called the Rayleigh-Ritz. And let me again explain what I meant to say with all those words. Say I'm not interested in finding the exact solution to this equation because it's a lot of work. Perhaps what I can do is plug in into this equation instead an approximation. Say it's W naught, W C0 plus C1x plus C2x squared. Say that's the one I plug in, which I can, by the way, because it's sufficiently derivative, differentiable. The order of differentiation allows me to substitute this equation in here. Guess what? When I plug that in there, pi just becomes a function of those constants only. That's it. And so as a consequence, I can just use regular calculus. Derivative of pi with respect to C naught equals 0. Derivative of pi with respect to C1 equals 0. And derivative of pi with respect to C2 equals 0. This will give me an algebraic system of equations, which allows me to find C naught, C1, and C2. And guess what? This W is the one that does the best job at minimizing pi, but it's also the one that does the best job of solving that equation approximately. So they are connected. They are connected, and that's an amazing thing because I can now start from total potential energy to solve this equation. Okay, that's the idea that we'll be discussing today. Okay, and that's an exciting moment. So my idea here is I don't want to solve governing equations by pulling a book and finding the exact solution or going to mathematics and solving a solution. I want to find an approximate solution. So I'm going to select an approximation function just like I did for the weak form Galerkin, which is this like that. So I'm going to take a W that's equal to phi naught plus a summation Ci times Phi. And this phi naughts and Phi's are again selected very carefully. Okay. And they're selected carefully to meet the criteria I discussed before. Like in the weak form Galerkin. I'll substitute this into, say I have this beam under a distributed load. The total potential energy for that problem is this one. If I substituted this approximation into here, I'll get this. Now notice how pi ends up a function of these c's only. But these p's are known. These p's are like x, x squared, and so forth. So check that out. I can just take the derivative of pi with respect to c1, the derivative of pi with respect to c2, and so forth. I get n equations and unknowns, and then I can solve for c1, c2, up to cn. And if I know that, then I know the approximate solution to the governing equation as well. And why is that? I already told you that the strong form, from the strong form, we develop the weak form. Minimization of total potential energy implies a weak form, but the weak form comes from the strong form. So therefore, minimizing pi relative to an approximation you make on W is also solving that equation indirectly. That's what we're talking about here. And I have n equations and unknowns that allow me to find the c's, and therefore I have a way of approximating a solution now. In my book, I have several examples, but I'll be covering different examples from my book because I think that gives you even more room to play in terms of knowledge. The approximate solution to this algebraic system of equations also is the one that approximates the solution to the PDE and corresponds to the deflection field that minimizes the total potential energy. The Rayleigh-Ritz approximation has to follow the same guidelines as the weak form Galerkin. Remember, the strong form Galerkin required the approximation function to meet and satisfy exactly the essential and natural boundary conditions. In the Rayleigh-Ritz approximation method, each basis function must be continuous and differentiable. The approximation function has to be sufficiently differentiable. So in this case, a w double prime squared, we need an approximation function of the quadratic form. The basis function must be complete and linearly independent. And the approximation function selected must satisfy the essential boundary conditions. And the basis function must satisfy the homogeneous form of the boundary conditions. But we need to just satisfy the essential boundary conditions, just like in the weak form Galerkin. So let's look at this example problem. Consider a clamp beam under distributed load. The approximate solution satisfies the essential boundary conditions of this problem. So in this case, this is example number one. And here you can see that my approximation function is this one. And that makes sense because it's a clamped beam. And the essential boundary condition for a beam that's clamped is W naught at 0, 0, W prime at 0, 0. And you can see here that if I perform these checks, this approximation function is excellent. And if I plug this into W tilde, now the pi's, you can see here, become just a function of C1 and C2. And then I can just take this derivative and solve for C1 and C2. You can see here, I did it there. In Mathematica, I put the approximation function there. I said, hey, use this W in these integrals. So that's that. And then I got this algebraic equation. Then I take the derivative of pi respect to C1, and then there's the pi respect to C2, which is showing up here and here. And Mathematica does that for you. And I said solve it for C1 and C2, and I got the solution. Guess what? Guess what? That C1 and C2 that you see there at the bottom, okay, when plugged in into this approximation function, that's the one that does the best job at solving the governing equations for the problem. But it's the one also that minimizes pi. Another example, I have a Rayleigh Ritz example problem of now I have this additional deflection here, and I have a load applied here. Recall that I have to have a W naught here for phi naught because W tilde equals phi naught plus the summation of Ci phi x. That phi naught there is for non-homogeneous boundary conditions, and you can see here I have one like that. So W tilde at 0 has to give me W naught, and you can see that works out. This goes to 0, this goes to 0, but this stays. And I need that there. I need something there that counts for that. So that's what the phi naught is there for. That phi naught that you see here is to account for those situations. And so again, I'll plug that in here and here, and when I solve it for the situation of a clamped beam under a load, point load, and notice here that the this energy stored in the beam, but there's a potential energy due to the load applied on that particular location, which is P times W at L. That makes sense. That's different from here, where I had a this is different from this situation where I have a clamp beam on the distributed load Q. That's why you see an integral from 0 to L because that Q is applied all along the whole length. Here I have a point load, and so that's why I don't have an integral because it's a point load. Okay, but bottom line is when I plug that in and I do these derivatives, I get the same answer as I got last week for the week from Galerkin for the exact same problem. I also did it last week for this problem, and I got the same answer using the week from Galerkin. So that's a deflection that I get. I get C1 and C2, and that goes in here, and I'm able to find a deflection that minimizes pi, but also solves the governing equation for that beam. Example 3. Example 3. Let's consider this functional that you see here above. Let's find u that minimizes f. Again, same procedure. Take u, anywhere you see u, put u plus epsilon v. Anywhere you see that. And then expand it very nicely. Expand the whole thing. Here, this is squared, okay? The derivative of this respect to epsilon, there is no epsilon here that goes to 0. The derivative of this respect to epsilon is just that, going to 1. Here you're going to get a 2 epsilon v squared. That goes to 0. This one goes to 0. So you get these terms. Okay. Now set it to epsilon equal to 0, and you get this equation. That's how you do that step. And so this is what I get. And that's what you see here. But last week I discussed this problem. Last week for the week from Galerkin, I started with this. So hey, let's derive the weak form. I multiply this by v. I brought this to this side, create a residual r, make it orthogonal to v, split the derivatives in two so that some goes to v and some to u, so half and half. The bottom goes into the integral, the cross term goes into the boundary term, and I impose the boundary conditions. In this case, look at this. So I have v. I did it last week, but I'll do it again. VL times u prime at L minus v at 0, u prime at 0. Um, u prime at 1 is 0 based on this. And u naught at 0 is 1. So that means this is going to go to 0 because it's essential boundary condition. Okay. And so that's what we discussed. And so um, I'm able now, I quickly derive the weak form, and I did it last week, but I'm doing it again here. You can see that this equation matches that. And this came from this functional. In my book, I explained how to derive these functionals from the governing equation, but I'm not going to ask you to do that here. But this here, minimization of f respect to u, this function u, we went through that procedure and found the weak form. We got the weak form somehow. And starting from the governing equation, I develop the weak form and I get the weak form, which is exactly what you see there. In other words, minimization of u of f respect to u is the same thing as solving this governing equation. And for that particular problem, I can select again, I can select an approximation function. Let's select this one. And that one is very nice because satisfies this boundary condition. We can check it. I did it last week, but we can check it. U at 0 is supposed to be 1. That's exactly what I get. U prime at 1 was supposed to be 0. That's exactly what I get when I do it. And so that's beautiful. We've able to achieve something powerful here. That's very, very neat. So now I plug this equation into the functional. This u tilde, I plug it into here, this right here, and I get this equation. And the derivative of f respect to C1 and C2, set that equal to 0 and solve for C1 and C2. And guess what? I did it here. I went through the procedure. I got this. And if you check, you'll find that we got the same answer as last week. So I found C1 and C2 that not only solve this governing equation right here, but also minimize pi, this f, I'm sorry, this functional f. And you can see here the weak from Galerkin gave me this same answers. Weak from Galerkin gave me the same answer as Rayleigh-Ritz. And that makes sense because the Rayleigh-Ritz is applying to the functional, but the minimization of the functional gives you the weak form. And so that makes sense, it's matching. Another problem, Rayleigh-Ritz of a bar, say that I have this distributed load applied. The approximate solution I'm selecting is going to look like this because it's fixed here. So u at 0 is 0, so C naught has to be 0. So I end up with this equation, this phi1 and phi2. So let's look at that. Go ahead and plug it in. Plug this into this here. The modulus varies because I wanted the modulus to vary just for fun. And then calculate the derivatives to find C1 and C2. This we already discussed is 0. And I did that here, minimize the respect to C1. I did it by hand. I get that equation number 1, which has C1 and C2. Now I'll take the derivative with respect to C2. Let Mathematica do it, but I'm doing it here so you can kind of see it differently. That's my second equation. Two equations, two unknowns. C1 and C2 are the unknowns. Solve for C1 and C2, and I get this. Now that I know the deflections, I know the strains, because the strains are du dx, which is that. And the stress is E times epsilon, so I know how the stress is distributed in that bar. So once I know the deflections, I can calculate strains. Once I know strains, I can calculate stresses. That's kind of cool. Another example 5. Say it's fixed here and fixed here. Okay. What do I have there? I have that the essential boundary condition is u at 0, 0, C naught is 0, so that goes to 0. But I also know that the boundary condition 2 is u at L is 0 also. So I have to solve for one of them, and I did. And my approximation function looks like this. I covered that last week, but I'm repeating myself. And again, I'm going to select an approximation function. And when I plug it in, I solve for C1. When I plug in u tilde in here, um, I can then take this derivative with respect to C1 and solve for C1, and I can then solve the governing equation for the problem. So in summary, I covered the following. The minimization of a functional with respect to a function implies a weak form, which is a strong form of the problem. The solution to a strong form of the problem is the one that minimizes the functional. Therefore, substituting an approximation function into the functional and minimizing the functional with respect to the unknown coefficients indirectly approximates the solution to the strong form. The Ritz method requires, however, the formulation of a functional. And it has the same requirements for the approximation function in that it needs to be completely linearly independent. The basis functions or the trial functions have to satisfy the homogeneous form of the essential boundary conditions, and phi naught has to satisfy the non-homogeneous form of the boundary condition. Again, an exciting way of doing this, completely different way, and a way that you're going to be working on in the future. I do want to conclude that the Ritz method, it is convenient for many physical problems where the functional is well defined, and you can find it. You can actually find it. Okay. So with that said, I thank you for listening, and have a great rest of your day.